Hello, everyone. We'd like to thank you for taking the time to join us in our 2021 web series. Today's event is the new linear accelerometer from DTS, where you will learn about our new A64C linear accelerometer in a rugged industrial standard enclosure. Before we get started, I'd like to cover the format and a few logistics. The webinar will be a slide presentation with audio and video from the presenter only. We encourage you to submit questions through the presentation by typing them in the Q&A window. You should see the button at the bottom of the screen. We have a panel of experts that will monitor and answer questions throughout the webinar. We will also be scanning through the questions at the conclusion and answer as many as we can, time permitting. If there is a specific topic that you would like to cover directly in a private meeting, please reach out and coordinate with our sales team. We are interested in learning more about and helping you with your objectives. Next slide, please. Your presenter today is Steve Pruitt, our CEO and DTS co-founder. The panelists for today's event are myself, Chad Ivan. I'm the Sales and Applications Manager for Crash and Safety, and Mike Beckage, our CTO and also a DTS co-founder. And now I'd like to turn it over to Steve to give you more information about this exciting new product offering.
Good morning and good afternoon and evening or whatever time zone you're in. I think we have folks from all over the world today, so I appreciate everyone being here. Hopefully we can provide you some good information on a couple new products we have at DTS. And as Chad said, enter your questions in the chat and we will try to answer all that we can. So I'm going to dive right in here. First slide, this is me, believe it or not, some 30-some years ago. This is at a crash test facility that the three owners we all met at, called Mobility Systems, about 100 miles north of here in the desert. They are now Carco Engineering, and they were recently purchased by IDIATA, but they are still a full crash test facility. We work with those guys all the time. So back 32 years ago when I started this, of course, we used crash test accelerometers. Endevco 7264s with no A, no B, no C. These were the very early 7264 accelerometers, some that are still used today. My job here at DTS is I'm CEO, but a lot of what I do is what we call business development. So I work on new products, including these new sensors. So I'm happy to present these to you today. All right, so these are the things that I'm going to cover. First, a little bit about accelerometer, measurement fundamentals. Then we'll dive into the DTS new designs, a couple application examples, and then just a little bit about DTS resources. Okay, acceleration. That's what we're trying to measure here. That's what we're talking about today. There's a number of different types of accelerometers, and I haven't listed all of them here. I've only got a couple of them, but I wanted to kind of go through the summary of these two types to kind of give a little bit of background of the type of accelerometer that we are offering and that we produce and other types. So two main types of accelerometers are what we would call piezo-electric or piezo-resistive. And a piezo-electric is generally a crystal that responds linearly to a force. So you have a mass which either compresses or shears a crystal, and it outputs a voltage that is linearly correlative to acceleration. Now these accelerometers are used a lot in aerospace applications. They're very good for vibration. They're good at high temperatures, which is important in aerospace. The one thing is they don't have what we would call DC response or low end frequency response. You'll see in the chart there, I have around 5 hertz is where they drop off. What this means is you can't measure gravity. You can't turn it over and measure 2 Gs with this type of accelerometer. It'll eventually just zero back out. On the other hand, a piezo-resistive accelerometer, as you can see on the right in that simple diagram, kind of a mass on a beam there. And if you put some strain gauges on that beam, gravity will act on that mass and will stay there. It'll be static. You could measure 1 G in one direction and flip it over and read 1 G in the other direction. And so that's what we call DC response, or down to 0 hertz. And then you can vibrate that beam and it'll have some frequency response up to a certain frequency level. And then there might be some resonance points, which we'll talk about. These are good for tilt applications, for shock applications, and most importantly for vehicle crash testing and biomechanics injury calculations in general. We typically want to know what to integrate acceleration to determine velocity, or delta V. And if you use a piezo-electric transducer like on the left, and you don't have DC response, the integrated acceleration data generally is not very accurate depending on the type of pulse. And in our world, typically we're looking at one crash pulse, one impact, whereas with a piezo-electric, a lot of times you're looking at vibration over continuous time. So a little bit closer look at what we would call a piezo-resistive sensor technology. I think most of you are probably familiar with a strain gauge. A strain gauge is a very fine set of wires that are generally adhered to a metal beam. And if you compress or you put it in tension, that wire becomes either longer or shorter, and that changes the resistance across the wire. And we can add electronics to that, and we can measure that resistance. And then with a data acquisition system, we can capture that change in resistance as the voltage changes across that wire. So that's what a typical strain gauge does. And that's why for an accelerometer, you can call that a piezo-resistive accelerometer if we use that same kind of methodology. So piezo-resistive accelerometer can be thought of like a strain gauge load cell. Again, the diagram on the right, top right there shows, again, we have a mass, we have a cantilever beam, we have a strain gauge. But how do we do this in practical application in a sensor? You can see on the 2 diagrams we have here that there's types of sensors they call a MEMS sensor, and I'm sure you've heard that term, micro electromechanical system. And essentially what that is they've found ways to etch into silicon very complex structures that can move. Some are fixed, some are movable, and they essentially have the strain gauges, as we're talking about it, on some of these movable plates. Now, again, these are pretty complex structures in there, so they can have many, many movable plates in there, and they can sum these resistances and do things that make it an accurate, acceleration, an accelerometer, in fact. And you can see on the left, this is how it might be packaged. It might be packaged in a very small sensor that you can actually put onto a circuit board, or you can attach wires to. So let's talk a little bit further, and let's talk about capacitive accelerometers. So as I said on the last slide, you have a very complex silicon structure in there with many arms and movable plates and fixed plates. But instead of putting essentially strain gauges or measuring the resistance change, you can also measure the capacitance change. And so in this diagram, you can see, again, this is a pretty simplified diagram because the actual MEMS transducers have many more arms and structure to them. But if that mass moves with acceleration, then the capacitance between the plates change. And this can also be measured and made linear to the acceleration so that we can have a sensor that we can use in these shock applications. It turns out that a capacitive-based MEMS accelerometer, they've found ways to make this quite a bit more accurate than a piezo-resistive where you're measuring the resistance change. They can do a better job measuring the capacitance. They also tend to have, MEMS tend to have a temperature sensor, and they can do some offset compensation inside the transducer itself. We'll talk a little bit more about that in a minute. So looking just a little bit closer in on a capacitive accelerometer, the diagram on the right, again, shows a simplified version of movable plates and the capacitance changing and how we pick those capacitance measurements off of the moving plates. And then on the left, you can see this is a zoomed in look at, I'm not sure if it's an actual MEMS sensor or a CAD image of it, but you can see that it's a very complex image. And as I say here, the plate distance can be like 0.0013 millimeters, and the whole moving mass could be, less than a microgram. So very small structures, but over time, the manufacturers of these have gotten really good at making them. And it's no wonder that the advent of cell phones and the accelerometers and angular rate sensors you have in every cell phone, there's been hundreds and hundreds of millions of dollars of development into making these small sensors. All right. Some important specifications. There's a lot of things that we have to think about when we're trying to make, a good accelerometer. And it depends certainly on the application, and there's a wide range of applications for accelerometers. In the automotive safety realm, we're looking for a number of things. Certainly, we want DC response, as we said before, and we want it to be linear over a frequency range, and a lot of times we call that the frequency range of interest or the bandwidth. So that would be 0 hertz, at least out to SAE class 1000, but actually we're going to have our accelerometers generally want them to be out closer to 4,000 or 5,000 hertz, and we can do software filtering, with the data later. Now, all mechanical structures have a resonance point, and these are no different, even though they're really tiny mechanical structures, they still have a resonance point. And there are certain accelerometers, and originally most accelerometers were what we would call an undamped accelerometer. And in those undamped accelerometers, you typically have a frequency response somewhere out around 20, 30 kilohertz. And these can go into resonance, and they very easily go into resonance at those frequencies. And that resonance can cause some errors in the data. It can also saturate amplifiers on data acquisition. And so there's some disadvantages to undamped accelerometers, especially in this application. And a lot of the accelerometers used in vehicle crash tests now are what we would call a damped accelerometer. So they're trying to, above a certain frequency range, we're trying to dampen out the motion in those higher frequencies so that the resonance point, which will still be there, will be attenuated out at those higher frequencies with the damping. That damping could be oil damped, it could be air damped, it can also be electrostatically damped. It depends on the accelerometer technology, how that is done. If we look at SAJ211 and SA2570, these give some guidance on accelerometer specifications and what you're looking for. So I'd suggest if you haven't looked at those to go ahead and take a look. On the right side, I just throw this out there because this is an interesting note for myself. We actually had a contract years ago with the Norwegian government to come up with a seismometer that would go on the bottom of the ocean. And it was a very interesting project because we had to keep 1 millisecond timing accuracy across non-connected modes for a month, which was quite a challenge. But one of the things we learned at the time was for seismic measurement, you use what's called a geophone, which is a really simple accelerometer. It's a mass and a magnet and a coil. And on that spring, it just moves up and down. And it turns out that even with today's technology, as much as they've done with MEMS and different technologies for accelerometers, this is still the most accurate way to measure seismic events. It's down in the nano-g of performance, and you just can't get that with a MEMS accelerometer. All right, let's move on. So let's talk a little bit about the DTS New Accelerometer Designs. So first of all, for DTS, we make a number of products, I think as most of you are aware, and we tend to categorize these into 3 different areas. So first of all, data acquisition systems, in the way we define it, are systems that the sensors are plugged in externally. So if you look up on the top left, our Slice Pro system, each of those sensor input modules has 18 connectors in it, or 18 channels you can connect. And we also have an array of other data acquisition products, the T-G5, the Slice Nano and Micro, the Slice 6, and the newest product we have, the Slice 6 Air. For data loggers, our definition for that is essentially a data acquisition system that also has integrated sensing. So our TSR Pro that we've made for a long time, the one in the middle there is our Slice HG, we call it. That's actually used for gun launch, like very high acceleration, 25,000 Gs. And then our one of our newer products, this our mouth guard sensor, which is a 6 degree of freedom sensor and data recorder that's used in the NFL for looking for head impacts. The final category of things that DTS provides is in the sensor category, and these are truly sensors. They can work with DTS products, but they can also be plugged into other data acquisition systems, and customers do that all the time. Now, we're pretty a niche player in the sensor market. We're trying not to compete with larger sensor companies. We're very much focused on the application of higher shock, short event, applications where customers are trying to do biomechanics testing or other things like that. So if we look a little bit closer at what we've done, the ARS, or the angular rate sensor that we offer, we first came out with that in 2011, and that was originally developed because the NHTSA came out with a standard for measuring seat back angle in a rear impact, and it was very hard to actually physically measure that angle. And we determined that if we had a quite accurate and dynamic angular rate sensor, that you could integrate that data and determine the angle quite accurately. And so we started selling the ARS sensor, and I want to emphasize our angular rate sensor is really for a dynamic environment. It's really good at measuring angular velocity while also in a high G environment, which is pretty rare for an angular rate sensor. It is not good for guidance. We have customers that say, what's your drift spec? How many arc seconds over, so many minutes does it drift? And we're like, that's not us. That's an IMU. That's used for guidance. We are for short impacts where we're trying to measure accurately the angular velocity, in a high G environment. And then at some point we came out with what we call a 60X sensor. So this is 3 angular rate sensors and 3 accelerometers all in a very small package. And the one that's you see there, called the 60X Pro, is actually used a lot in biomechanics testing, in cadaver testing and things like that, where it really needs to be a small package. That's only 19 by 19 by 14.5 millimeters, that 60X Pro. When we came out with the Slice 6, we created a new 60X package that would plug directly onto the Slice 6 data acquisition system, as you see on the right, which makes a nice 6 degree of freedom data recorder package all in that little space there. I note here we make angular rate sensors that actually go all the way up to 50,000 degrees per second. In case you're wondering, that's basically ballistic rates of turn. The only way to get that is in a blast kind of environment, which is why we developed that. It's been used at Aberdeen Proving Grounds quite a bit for measuring rotation in blast environments. All right, so moving on to our new accelerometer design. So we had a problem with our 60X, what we call G2 sensor, because the 2000G accelerometer element that we're using was going end of life. And to be clear, DTS does not manufacture MEMS accelerometers. We don't have the expertise or equipment. This is a multi-billion-dollar kind of industry that takes very sophisticated design and manufacturing. We actually partner with companies that make MEMS sensors. And again, most MEMS sensors are made for your cell phone and are certainly not the acceleration range or frequency response we need. So we have to work with MEMS manufacturers that can and do develop accelerometers in the ranges of acceleration and frequency that we're interested in. But the 2000G accelerometer element that we were using was going end of life, has gone end of life. And so about a year and a half ago, we started working on developing our new MEMS accelerometer for this. And its maximum range is 500 Gs. And so there are going to be some customers or applications where the new accelerometer won't work because we don't go to 2000 Gs anymore. But for vehicle crash testing and ATDs, crash dummies specifically, there really is no acceleration components over that 500 G range in a typical crash test. The only time we've seen that is when we do blast testing. DTS, the underbody blast mannequin that we make in the lower extremities and the legs and the feet, we do see some acceleration levels above 500 Gs. So we created a new product, which we call the 60X A2 instead of the G2. It's, again, identical package-wise and how it works to the old 60X G2. The only difference is that it's 500 G range instead of 2000. And we also think it's a much more accurate sensor. We think the noise is better. We think a lot of things are better about its performance, but the acceleration range is less. And we started shipping those A2s actually back in December. So those are a product you can order today. They are also come in the same options for angular rate sensing, because remember, these have 3 angular rate sensors and 3 accelerometers. So those angular rate sensors can still be ordered in either 8,000 degree per second or 18,000 degree per second ranges with either 600 hertz frequency response or 2 kilohertz frequency response. For those of you who use our 60X Pro sensor down on the lower right there, no changes there. We are going to continue to offer that in the 2000 G range and not the 500 G range. We have basically done an end-of-life buy on the accelerometer elements that we have, and we have many years of supply for those to create that product. We understand in biomechanics and some other applications that having an accelerometer that will go to 2000 Gs can be important. All right, so just a little bit more about the DTS accelerometer design here. Now, there are some sensors we would call an active sensor versus a passive sensor. Looking at the passive sensor first, we can think about this as a Wheatstone bridge, like a strain gauge type sensor. If you have a Wheatstone bridge, if you have 4 resistors in a Wheatstone bridge and one or more of those resistors is changing its resistance based on the acceleration, you can measure the resistance changes, and this would be called basically a passive sensor. All it takes is excitation voltage, and you have a signal that comes from that change. Now that signal will be quite small, and you have to put a fair amount of amplification on that when you put it through your data acquisition system. But this is the way sensors have been done for a long time, and that works quite well. A lot of newer sensors are what we would call an active sensor or an active accelerometer. So you might have a similar sensing structure. In this case, I just simplified this as a sensor bridge. But in the package itself, you will have some electronics that will do some amplification, that will do some filtering, will do some temperature compensation. And this is typically done in what we would call an ASIC, or an application-specific integrated circuit. So this is a very small piece of electronics. So if you were to take the cap off a MEMS accelerometer, you would typically see two main pieces in there, pieces of silicon. One would be the sensing element itself, and the other one would be this ASIC in there. And so what we get with an active sensor is we get a higher output level, a cleaner signal. And then with DTS sensors, we also add some more electronics around the MEMS sensor to provide for a wide input range for your excitation voltage. And so it's not, now it's not proportional to excitation. You can put in anywhere from 4.95 to 14 volts, and you still get out the same sensitivity, in this case, 3.75 millivolts per G for our sensor. So we'll see that this gives an active sensor gives, better performance over temperature. It gives better noise performance. And you don't have to run your data acquisition system at quite as high a gain. And so typically the noise level in your data acquisition system itself is lower. So when we were developing the 60X-A2 sensor, this was where, again, our 6-degree of freedom sensor, where we put 3 accelerometer elements in. And we put a lot of work into characterizing this new 500G MEMS sensor element. At some point, we decided, maybe we should look into making a single axis sensor instead of just a 60X sensor. And for those of you who are familiar with the vehicle crash industry, this is a very common looking package. Again, this has been around since I started crash testing 30-some years ago. This 7264 style package with these dimensions, using those type of fasteners, the 080 screws. This has been around a very long time. And so we looked at our accelerometer element, and we tried to see if we could make a sensor like this that would fit into this standard package, and we were able to do that. And as I think a lot of you know, we do a lot of ATD integrations now. We do a lot of work with ATDs, and so we have some need for these types of accelerometers. And we were actually having a fair amount of trouble with lead times in getting supply of these accelerometers from vendors for these accelerometers. And so even for our own business, we were just having trouble with supply. And so one of the main reasons to come out with this accelerometer was so that we would have our own supply of single axis accelerometers for ATD integrations. Now, again, this is an active sensor. We believe it has better drift and noise specifications. We can offer these as pigtails. We also, of course, terminate connectors, LEMO to G-magnetics, pretty much anything that a customer might need, and any pinout. We also install sensor ID chips, used a lot in the crash test industry as well. Now, the A64C, unlike the 60X-A2, which has been in production and shipping since December, this one tails the development a little bit there, and we're hoping to ship these in May-June timeframe. We're finishing up some testing, finishing up some qualification, and we're moving this over to the production side of DTS. We really want to be able to stock quantities of these so we can ship them right out of stock. We understand our customers, especially for sensors, and this is true about our angular rate sensors, that people generally want pretty fast turns. So we try to keep stock of those so there's not a lead time issue. So just a quick look at some of the specifications for the A64. Again, this is draft. I put draft on there on purpose because we're still, working on these. And we do have a data sheet that goes along with a full data sheet. Again, not quite ready to release, but we're almost there. So just a couple important things. Bandwidth 0 DC hertz, DC response out to 5,000 hertz. Again, it has an excitation voltage where you can put anything in from about 5 to 14 volts. These other things are pretty typical: linearity, transverse sensitivity. We are looking at a 1% option. That has to do with alignment of the sensor. So we want to make sure that, we're not getting acceleration from a cross-axis hit. When you see acceleration in the off axis, you don't want it affecting the actual axis of the sensing axis of the accelerometer. Damping ratio, we'll talk a little bit more about that in a minute, but this is a damped sensor. And the rest of these, it's low current. Again, the output nominal sensitivity, 3.75 millivolts. That's higher than a passive sensor. This is you can do a shunt check with this sensor as well. And also we are rating this at IP67. So for those of you who do cadaver testing and things like that, yes, you can put them in cadavers and they will work just fine. All right, let's just look at a couple of the performance tests that we've done here. Again, a couple competitors out here, you can see the noise level is maybe about half on the A64C. Again, this is a sensor where you are putting some amplification right at the sensor inside the MEMS package with an ASIC. So you tend to get a better signal out of it, a higher level signal here. Also, the stability of the accelerometer just in shock. We've done some testing in an outside laboratory, Boucher Labs, where they do a calibration on a shaker, on a calibration shaker, and then they do some shock, and they can do some comparisons. And the A64C does very well in these types of tests. And then just basic drop test. Of course, we do a lot of drop testing here at DTS. We have a number of shock machines of different size and accuracy. And so one of the things we do, regularly is just back-to-back drop testing. It's very important when you compare accelerometers that these are placed, the reference or the one under test is directly on top of each other. If you put them side by side on a drop tower, you can get different accelerations mechanically. So we do back-to-back drop testing. And you can see in this case, we have compared an undamped 7264C accelerometer with the A64C from DTS, which is damped. You will see a slight change in the a delay in the pulse there. And this is expected because of the damping, but it's on the order of about 30 microseconds. But you can see the pulse shape and the amplitude are nearly identical. I mean, as far as when we do a class 1000 filter on a drop test like this, I think anybody who is going to, use one accelerometer versus the other would believe this is an equivalent, sensing device. So now if we flip to the next side here, now we're looking at unfiltered data. So we're sampling at a pretty high sampling rate. The filter is out at 40 kilohertz, the anti-aliasing filter. Now you can start to see the resonance of the sensors. And you can see with the 7264C, we can actually measure, like I have there, if you just measure the time between the peaks, it comes out to a calculation of 26.7 kilohertz, which of course was what we expect because that's what's on the data sheet for this type of accelerometer. It has a resonance point out about that area at 26 kilohertz. Now, the damp sensor, as you can see, the DTS A64C, you don't see that resonance. It hasn't gone into resonance. You do see it's not a perfect sine wave because this is a shock tower and it doesn't produce a perfect sine wave. So that orange trace there is likely the actual acceleration that you see. As we said earlier, undamped accelerometers, part of the problem is when they go into resonance, they can swamp the input amplifiers on a data acquisition system and cause some issues with measurement. So looking at a frequency plot of a 7264C versus the damped sensor from DTS, you can see, as expected, around 27 kilohertz, you get a resonance point, which is quite high because it's not damped. And so even though it's past the range of interest, from the frequency standpoint of what we would like to see for vehicle crash testing, it's so high out at over 50 dB that it can affect the data. On the blue trace, this is the DTS A64C, you can see the sensor that we have, the MEMS accelerometer that we use, has a resonance point a little bit further out, actually at 45 kilohertz, but it's damped, and so it's actually less than 10 B of amplification there out of its resonance point, so which really doesn't become a factor in any of the data that we're looking at the lower range. Now you can see on that blue trace that at around -3 dB, we're basically flat out to about 4,500 hertz or so. So way beyond the SAJ211 range, which is the dotted lines there for a class 1000 filter. So typically customers would collect this data, say at 20,000 samples per second with maybe a 4 kilohertz anti-aliasing filter. And then post-test, they might filter it again down to class 1000 into this corridor. So you want your accelerometer to have, even though it's damped, you do want it to have a flat frequency response out to that 4 or 5 kilohertz kind of range. All right, just a couple application examples here. So as I said, DTS, we do a lot of ATD integration for in-dummy DAS now. Our new Slice 6 data acquisition system that just came out a couple of years ago or so was designed originally for the Weeman Army underbody blast mannequin, but we have transitioned it to use in most all automotive ATDs as well, Thor, World SID, ES2, the Q series, etc. And in a lot of locations there, we use a Slice 6, which is plugged directly onto our 60X-A2. But there's also many locations where we might need a single axis sensor. But part of that process is we do that full integration service, and then we provide the customer users manuals and being able to work on the dummy in a maintenance manual so you can take it apart and do your calibrations, et cetera. That's a kind of a full service ATD integration that we offer at DTS at this point. And so, as I said, we offer this in pretty much all the ATD types. You can see in the middle there's an example of a Thor dummy that we received from the customer on the left with all its external cabling. And this is like literally like 12 kilograms versus of cabling that would be coming from the ATD and being plugged into a on-vehicle data acquisition system. So when we get that ATD, we eliminate all that wiring. We cut all the wiring to an appropriate length for all the sensors. So now they're terminated into a Slice 6 data acquisition system, which is internal to the ATD. We call this a no-mass solution because we do adjustments very carefully to the ATD structure so that we're not changing the mass or the moment of the ATD, but we're adding the electronics in there so that the ATD, you're not having to add this mass of the cables or the on-vehicle data acquisition system to do your testing. Also, obviously, much more convenient because now you have one connector that you plug in with power and Ethernet. But as we said, you can see on the lower left, this is like a head application where we have a Slice 6 connected directly to a 60X-A2, and we might want to measure in the head a 6 degree of freedom measurement with 3 accelerometers and 3 angular rate sensors. But there are applications where we need single axis sensors, which is why we came out with our A64C sensor. And so applications for that, there are a lot of customers who still prefer single axis sensors or maybe they don't need angular rate sensors. And so this is just a typical application here in a head. This is a standard accelerometer mounting block that again has been around for a very long time. Our new A64C sensor dimensionally fits in all the locations that a sensor of this type would fit in an ATD. This just shows 3 accelerometers on a triax block in a standard head. And as I said, our sensors, just like our angular rate sensors, our new accelerometers work with all DTS products, but they also work with other data acquisition systems out there. Again, anything that can provide anywhere from 4.95 to 14 volt excitation and a 0 to 5 volt input range. The DTS accelerometers will work great. Wrapping up here, just a quick thing about some DTS resources. We do offer calibration. We use a modal shop unit here that we purchase, and then that is also yearly checked for its calibration and NIST calibration so that we can provide ISO 17025 calibration services for our accelerometers. We do have a station like this in our California headquarters and also our Michigan headquarters. And we are looking at offering acceleration calibration services in our European and Asian technical centers later this year. If you're not familiar with our Help Center, this is a great place to go if you have questions about our accelerometers or other products. I encourage you to register on the Help Center. Lots of good information there. We are adding stuff almost every day. Product manuals, data sheets, how-to guides, frequently asked questions, and you can enter a help ticket. And we have 24/7 technical support folks that can really dig into your application and help you out. I throw this up there because we are always looking for good people. And if you're interested, we do have a few positions open here at DTS. Go to our website, look for careers, and we are always expanding. DTS is a little over 100 people now, and we keep growing in this market. And we love to reach out and see if we can add to our team. Thank you. So I'm going to turn this over to questions. In fact, I'm going to go ahead and let Chad Ivan take back over. And if there's any questions or wrap up you want to do, Chad, why don't you jump in?
All right, thank you, Steve. We've actually had quite a few very good questions, and there still are a couple of questions that keep coming in. We're going to go ahead and continue to answer questions online using the Q&A session. And I'll go over some of the ones that have already been answered, and we've got like 5 in the queue at the moment. So we'll keep the webinar going until we've had an opportunity to answer all of these questions. But just to go back, there was a couple of questions that I'll highlight. There was a question about active sensors. Does the excitation introduce any inaccuracies within the sensor? And of course, Steve went through this a little bit in detail. The ASIC and the way of processing the excitation voltage, since we are excitation agnostic, we can have somewhere between 4.9 and 14 volts coming into the sensor. The value coming back is linear at that 3.5 millivolts per AG, regardless of what the input excitation is. So it's actually one of the beauties of this sensor is you can actually have a data acquisition system that's not as accurate on its excitation voltage and still get back a linear value based on the particular excitation, or based on the acceleration that's going into that sensor. Question about whether it meets the SAE J211 corridor, and Steve went through that and showed that we are flat well beyond the J211 corridor, so post-processing of that data to make it fit in the class 1000 corridor is not an issue. There was another person that had asked if it's a direct replacement for the 7264C, and I believe there's an open question about this at the moment too. Seismic mass is definitely extremely close to what a 7264C is. Any mounts that you use for a 64C or a 7264C, those are the same mounts that you would use with this particular accelerometer. Another person had asked about the amount of excitation current that's required. All DTS sensors use an extremely low amount of current. So the A64C, our accelerometer, uses 2 millivolts or 2 milliamps per an axis. And our ARS sensors, just as an example, use 4 milliamps per an axis. So extremely low. Pretty much any data acquisition system out there can supply the required amount. Somebody had asked about, does a accelerometer need to be calibrated on a regular basis? Now, this is something that's extremely company dependent. Your quality standard that you end up writing for yourself is what truly drives your own internal requirements for calibration. But the SAE in J211 does recommend an annual calibration. So a lot of people fall back onto that as far as how often you get the sensors checked out. But that truly is a company specific decision that needs to be made. And of course, our A64C can be calibrated at actually any lab that is able to calibrate a 7264 or a 64C. It does not have to be done at DTS, but of course, Steve went through and showed that we do offer ISO 17025 calibrations for those types of accelerometers. And we'll be opening that up more into Europe and Asia in the future. Somebody had asked about the presentation, if it's going to be available at the end, and that was kind of our final slide, but I'll say it now. We are recording this webinar and we will be posting it to our YouTube account. And we'd like to have you guys take a look at our YouTube, not just join our help center, but also take a look at our YouTube channel. There's a lot of great informational videos that are posted on there, including prior webinars that we've went through, including some of these questions and answers. And we would love to hear your feedback on the webinar and also ideas on other things that you'd like to see come from DTS. And let's see, what else do I have in here? Question about acceleration is 4 to 5 Gs. Should we use a piezo-resistive accelerometer? You can definitely measure the 5 Gs with a piezo-resistive type or a MEMS type of accelerometer. A lot of that's going to depend on the frequency response that you're looking for, though. And there are other models, of course, that do go much lower. We actually do have an IMU unit that we sell that has a 2, 5, 10G type of accelerometer that's built into it that has similar temperature compensation and stuff. So it's more of a inertial measurement unit as opposed to just a particular sensor, a specific sensor. Will the solution operate with a Messering supplied 3.3? Unfortunately, the answer is no. It will not operate below the 4.9 volts, but it is stable down to 4.9. Let's see, what else do we have? Is it a damped? Of course, it is a damped accelerometer. On our spec sheet at the moment, it's listed as 0.7 damping ratio. And question was, is it gas or oil? It's not oil, but it is some kind. I think it's a combination of different methods that are being used. We have to look into that a little bit more. And we still have 9 open questions that we need to answer. Is there a center of seismic? Is the center of seismic mass the same place as the 7264? I kind of mentioned that it is extremely close. The 7264 is an interesting one to talk about because just probably 5 or 6 years ago, Endevco actually came back and said, oh, by the way, our center of seismic mass that we've told you about for the last 15 years is wrong. It's now in this new location. So all M64 and 7264Cs or M, and they're all extremely close as far as where their center of seismic mass is actually at. Another question about during accelerometer calibration, what needs to be done? Frequency response, shock. Do we require transverse sensitivity during calibrations? Those are all excellent questions. That again is going to boil down to what you specifically want in your particular calibration that's being done. There are advantages and disadvantages. Frequency response type of acceleration ones, unfortunately, don't typically go very high in their acceleration. And depending on where you're at within the world, different countries / companies have different thoughts on this. So in Europe, it's typical to use a shock acceleration type of test, which is only a single pulse. It does give you a frequency, but it is typically in the at least 5% of the max range of the transducer, and more simulates how we would typically use it in a crash testing scenario. It still doesn't go to 2000 Gs on a 2000 G accelerometer. It may be 200 Gs, but it's kind of a company decision. We have the ability to do a shock test, and we have the ability to do shaker tests, and we also have the ability to do a steady state, much higher acceleration calibration within our company. What is the output current range? Not exactly sure about that question. The current that's used is 2 milliamps. And the overall voltage range is it's 3.75 millivolts per a G, and it's plus and minus 500 Gs. Let's see. I think that Humanetics has qualified this sensor for their dummies. Have they tested this sensor? We have delivered dummies with the 6DX A2s. The A64C is something that is very close to going into production. It is the same element, just in a smaller package size. So Humanetics has done some stuff with it as far as qualifying it. That would be a question probably more for them. Let's see, if the accelerometer cable is cut during a crash, is it advised to rejoin the cable and use the accelerometer again? Do we need to calibrate it before your next use? So this is going to come not specifically from DTS, but this will come from Chad and my experience. Putting a transducer wire back together is highly dependent on how good your technician is. If you have a technician that you trust in order to solder wires together, and also do some type of at least a 2G validation roll on that particular transducer, then I would say I would probably be comfortable actually doing that without having to recalibrate it. But if you have a cold solder joint on a particular wire, and if it's $1 million vehicle that you're trying to crash, I think I would send it back through calibration. So again, that's my personal input on that. bridge resistance. Actually, Mike is answering this one at the moment. I believe that we have an equivalent. We actually are able to do a shunt check, and it's very similar to our other active devices. So it's something like comes back with a 3,000 ohm equivalent bridge resistance when you're performing a shunt check. But since this is a variable capacitance transducer, that's actually being done through a separate circuit within the device itself. And I believe that that's probably going to do it for us at the moment. Steve, did you have anything else you wanted to add?
Oh, I think that's good. Thanks, Chad, for going through all those, and I'm sure there'll be more questions as we go along. And we're here, like we said, it'll be another month or two before we release this product. We'll have full specifications and a data sheet out pretty soon. But in the meantime, any questions that you have, please direct them to either our sales or our technical support crew. And as I said, we wanted this product for ourselves internally, the A64C, but we are seeing quite a lot of interest in the industry as well to purchase these outright. So we'd like to get any feedback we have from the field here and the applications. And we hope to be able to be a supplier for these for in the future. I think that's it.
All right, we'd like to thank everybody for spending the last almost hour with us. We appreciate that. And yeah, like Steve said, make sure you go ahead and submit a help center ticket if you have other questions, or contact your local sales representative, and we'll make sure we get back with you as quickly as possible. Thanks again, everybody, and have a great day.